if we if you take any bounded linear operator T on a complex Hilbert space H, then the numerical range is nothing but actually the mapping from the unit sphere of the Hilbert space H to the scalar field where X is going to inner product TXX. So that is very standard notation of denoting it by WT, and it's a collection of TXX. X belongs to H, norm X is equal to 1. So let us see how this set WT looks like for very elementary operators. So if you look at this operator as, for example, this nilpotent operator or 0, 1, 0, 0 matrix, then it's a very nice figure, and it gives you the circle with radius half. So very nice geometrical shape. And then if you look at this property of numerical range, especially when you are looking at the bounded linear operator T, then it is always a bounded set. In addition, if you think it is acting on finite dimensional space, then it will be compact. So these are very elementary results, and you can just use this Cauchy-Schwarz inequality to show the boundedness, and you can use very fundamental analytical property of a compact set, that the finite dimensional space unit sphere is compact and the mapping is continuous, X going to TXX. So the numerical range is also it's compact. But if you are working on an infinite dimensional space, then the numerical range may not be compact. So if you just look at this operator on L2, the left shift operator, all of us know this, x1, x2 going to x2, x3. In that case, the numerical range actually looks like a non-compact set, and it is actually open unit circle. So this is how the numerical range, the boundary is missing actually, right? So it is also circle with radius 1, but with the boundary missing. So this is not necessarily compact. So in case of infinite dimensional space, numerical range is not compact, but for finite dimensional, it is definitely closed and bounded, and so it's compact. There are some very elementary properties. If you look at two bounded linear operators S and T, and if you look at any two scalars A and B, then W of AT plus BI is AWT plus B. Then it's a unitary invariant. W of U star TU is equal to WT. These are very elementary results, fundamental results, I must say. And W of T star looks like this. And W of T plus S, it is subset of WT plus W of S. So these are some elementary properties of the numerical ranges. Then the most fundamental theorem in the study of the numerical range was proved by Toplies and Hausdorff more than 100 years ago, and that is about the convexity of the numerical range. If you remember those figures that we were talking of just before few slides, all of them are convex, and that is nothing special actually in case of any operator, bounded linear operator on a Hilbert space. We can prove that the numerical range is always convex. So first we'll focus on 2 cross 2 matrices or operators on two-dimensional Hilbert spaces. So let me get into this. So I will just elaborate on this proof because it's more of geometrical in nature. So if T is a linear operator on a two-dimensional space, then WT is an ellipse whose foci are the eigenvalues of T. So as you know, this numerical range is immediately invariant. So by Schur's decomposition theorem, we can take the operator to be of the form λ1a 0 λ2. So now we will proceed case-wise by looking at these cases. Like if λ1 equal to λ2 equal to lambda, then we can easily see that W of T minus lambda I is a circular disk with center at origin and radius half of mod A. So this is, then in that case, your numerical radius looks like this. When the diagonal elements are same and you have a non-zero element A at the super diagonal element. And if W1 is not equal to λ2 and A is equal to 0, that means you have a diagonal matrix like λ1, λ2 with λ1 not equal to λ2, then it will be straight line segment, and you can easily check that it looks like this. So it's a straight line segment joining lambda 1 and lambda 2. So that is also convex. And the most important case is when lambda 1 is not equal to lambda 2 and a is also not equal to 0, the most general case. In that case, we just translate it t minus lambda 1 plus lambda 2 by 2 into I, so that we get matrix of this form, r e to the power I theta a 0 minus r e to the power I theta. And in that case, doing some calculations and then considering this operator a is equal to e to the power minus I theta t minus this upon a, we can easily check that actually this numerical range looks like this. So doing some calculus and all these things, algebraic calculations, we can see that the relation is x minus r cos 2 theta whole square plus y square equal to b square by 4 mod b square by 4 sine square 2 theta. So this is a family of circles, and we take their union, and ultimately we get, taking this envelope of this family of curves, we get this relation. This is the what we were looking for. This is x square by r square plus mod b square by 4 plus y square by mod b square by 4 equal to 1. So it looks like an ellipse. So W of A is an ellipse with center at origin, and minor x is mod B. Major x is root over 4 r square plus mod B square, foci at r and minus r. So it looks like this. But this is not the operator we started with. We started with the operator t, and we have gone to the operator a, which is actually to the power I theta into t minus lambda 1 plus lambda 2 by 2 into I. So now we go back to the original operator. As we know, this W of AS plus BT equal to A of WS plus B of WT. So from there, the W of AS plus BI is equal to A of WS plus B. So from there, we go to this numerical range of T, and it will look like, geometrically, it will look like this one. So that is again an ellipse. So all of these are convex. So for 2 cross 2 matrix, not only it is an convex set, it is actually an ellipse. So that is what is actually this 2 cross 2 operators numerical ranges looks like. Now the question that will come, so this is WT more or less. So actually this was of operator this. Actually this was of W of e to the power I theta into A. So this is origin at 0. And when you come take this WT, then it looks like this. These are all geometrical, very simple, interesting. One can actually work for himself also. So now the question, some interesting follow-up of this question, these results will be like this. So if you look at these examples, very, very elementary example, just to motivate so young scholars who are there. So this is like, line segment joining I and 2 plus 3i. Then if you look at this one, so this will be an ellipse, circle, since diagonal elements are same. Here look at the diagonal elements, 1 plus I, 1 plus I. So it will be something like that. And if you take this one, 1, 1 plus I, 0 minus 1, then it will be something like this. Now, the question is, if the dimension is greater than 2, how does the numerical range looks like? Will it be convex? The answer is yes. So in general, for dimension greater than 2, the numerical range is not necessarily ellipse, but it will be convex. We will prove it in a short while. But let us see first, how can it look like? So if you look at a diagonal operator like this, twice I, 1 plus I, minus 1 minus I, then it will be basically the convex combination of these 3 diagonal elements. So it will look like something like this, twice I, minus 1 minus I, 1 plus I. So you can prove it very elementary, in an elementary way. That's not a big deal. So when the dimension is greater than 2, the numerical range is not necessarily ellipse, but it may be ellipse also. So we'll see later on how we can actually generate these figures. Now we give this general proof that numerical range WT of a bounded linear operator T defined on a Hilbert space H is always convex. So what we need to do to show that convexity? So we'll take 2 elements from the numerical range, like xi and eta that we have taken from WT. And we'll show that the convex combination of xi and eta, 1 minus t into xi plus t into eta, that belongs to Wt. So for that, if you take t equal to 0 or t equal to 1, that always belongs to Wt. So we consider t belonging to open interval 0, 1. Now, what is the interesting part of this proof is that we focus on these elements. We are not getting into any extra element. We have started with f and g. So we just take this combination f plus lambda g by norm of f plus lambda g. So these elements always belong to the unit sphere of the Hilbert space H. So for any lambda, this is an element of unit sphere. Now you look at this t of this element, f plus lambda g by norm of f plus lambda g, f plus lambda g by norm of f plus lambda g. So now if we can show that there is some t, small t belonging to open interval 0, 1, for which this relation holds, so then we are done. So what will be our role? Our role will be to show that. So maybe I should correct myself. What is our proof? Our proof is to show that for each t belonging to 0, 1, this combination 1 minus t into xi plus t into eta is an element of this form. So for each t, we need to find some lambda for which this relation holds. So this is the, trick of this proof. So we start with a t and we are looking for some lambda. Lambda is an element from the complex field, scalar field. So once we do some calculations, we can see that this actually leads to relation of this form, mod lambda square plus c lambda plus d lambda bar minus t by 1 minus t is equal to 0, where c and d are complex constants independent of t. So now lambda is a complex number, so you consider lambda equal to x plus iy. So if you take lambda equal to x plus iy, then you will get two equations. One is x square plus y square plus ax plus by minus t by 1 minus t equal to 0. And another is cx plus dy equal to 0. The first equation, if you look at first equation is the equation of a circle. And since the constant term t by 1 minus t is negative, so it shows that the circle contains the origin. So when I put x equal to 0, y equal to 0, this is negative. So that means from very elementary coordinate geometry, that means circle contains the origin. So this blue, actually this circle x square plus y square plus ax plus by minus t by 1 minus t equal to 0. And cx plus dy, all you know, is a straight line passing through origin. So cx plus dy is a straight line passing through origin. So they will intersect at 2 points. So that means these two equations will be satisfy these 2 points, those red dots. So that means that the relation that we have started with, so this relation is satisfied by 2 lambdas. So that means given a t, I can always find a element of the unit sphere of the form f plus lambda g by norm of f plus lambda g, which will give me this relation. So that means this set Wt is actually a convex set. So this is a very nice geometrical proof of convexity of numerical range. And there is another proof which uses these projections theorems actually. So if you look at two elements xi and eta as before, then you look at the subspace spanned by f and g. So as I said that actually we are focusing on those two elements f and g. So if you look at the subspace spanned by f and g and let P be the orthogonal projection of H on B, so that PF equal to F and PG equal to G, since it is an orthogonal projection on B. So now you look at this PTP operator. Then PTP operator is an operator from a two-dimensional space to two-dimensional space. So it will again be convex, as we have proved that two-dimensional operator set, it's an actually ellipse. So WPTP is an ellipse. So it contains the line segment joining alpha and beta, which it should be xi and eta, I believe it's a typos. So this WPTP is actually contained in WT. So now you can see that this is actually, this means that this line segment containing xi and eta is also in WT. So then again, it gives the proof of the convexity. So numerical range is always convex. Now we come to the main concept of numerical radius. So what is the numerical radius? So since numerical range is convex, so whenever you have a convex set, bounded convex set, so you can find a circle which contains that bounded convex set, right? So radius of the smallest such circle which contains this numerical range is actually numerical radius. So analytically speaking, this is W, small w of t is equal to supremum of modulus of txx, x belongs to sh or x belongs to h, norm x equal to 1. So if your blue portion is the numerical range, then your numerical radius is the dotted. This is your, circle with radius as the numerical radius, small wt. So this small wt is the numerical radius. So maybe I will say a few words here out. So what is the, if you look at this WT, okay, maybe I will just highlight that later on. So I follow this actually presentation. That will be better for you people to understand. So another notion is spectral radius. Spectral radius is the, supremum of mod lambda. Lambda belongs to sigma t, where sigma t actually is the standard notation for spectrum of an operator. So in general, spectral radius is less than equal to numerical radius, and that is less than equal to norm of the operator t. But that follows from the, Cauchy-Schwarz inequality, that numerical radius will always be less than equal to norm of t. So now there are some very interesting elementary results. One is that t is self-adjoint if and only if wt is real. And if t is self-adjoint, then wt closure will be closed interval small m into capital M, small m comma capital M, where small m is the infimum of this txx and capital M is the supremum of this. And if t is self-adjoint, then furthermore norm t equal to wt, and this is equal to maximum of this small of modulus m and capital modulus M. So these are all elementary proofs. I'm not getting into the details of these proofs. So you can have it in your textbook. This is just interesting. That's what I wanted to mention them. So I skip this. Next is this result. If wt is equal to norm t, then it will force spectral radius should be is equal to norm t. So if you can look at this is interesting actually. If you take actually what was the result, that RT less than equal to WT less than equal to norm t. Actually, you can see from the inequality, RT equal to norm t forces WT is equal to RT is equal to norm t. But if you look at WT equal to norm t, then it's not necessarily following from this inequality that RT is equal to norm t. So I can see Professor Fuad joining.
Okay,
Oh,
hello.
okay. Nice to see you.
Okay, thank you very much. I'm glad to
Yeah,
be
yeah,
here.
yeah. So, but here you see this WT is equal to norm T. It's forcing spectral radius equal to norm of this T, right? So it's again elementary proof. These are all actually available in any standard book on numerical ranges. But I just wanted to mention for those young scholars, if they are there, to motivate them. So if you take WT equal to norm T is equal to 1, then there is a sequence of unit vectors xn such that Tx and xn tends to lambda that belongs to WT. And again, you use this Cauchy-Schwarz inequality to conclude that norm of Tx tends to 1. Then you take T minus lambda xn square. So this tends to 0. So this implies actually lambda belongs to approximate point spectrum. And so the radius of spectrum is equal to 1 because, spectral radius is always less than equal to numerical radius, and your numerical radius we assumed it to be 1, and 1 is a point of the approximate point spectrum, so it closes the argument. And then there is another nice result. If WT is a line segment, then T has to be normal. If WT is a line segment, then T will be normal. So if we again look at these proofs, so these proofs are very elementary and very tricky. So if WT is a line segment, the W is a point on the line segment with inclination theta, right? Then this is contained in the, just you rotate it and translate it, this is contained in the real axis. So this will be self-adjoint as we have already proved. So from there, you can prove that Tt star equal to T star T. So T will be normal. So class of normal operators have some nice properties, and these are all this. Wt is equal to norm T, Wt equal to RT, and Wt closer equal to convex hull of spectrum T. All those actually properties have a very special role in this theory of, numerical ranges and numerical radius inequalities, and they are being classified as different classes of operators. I am not getting into that. So if you are working on a finite dimensional space, then the numerical range of a normal operator is always a polygon. So for finite dimensional spaces, you have to be very careful. So if you look at a normal operator on a finite dimensional space, so WT is always closed. So as from the result that we have just mentioned, that closure, this numerical range closure is actually convex hull of sigma t. This result I am mentioning, numerical range closure is equal to convex hull of sigma t for normal operator. It is true. So when you are working on a finite dimensional operator, then the closure is equal to the numerical range. So we get this result that WT is equal to convex hull of sigma t. And as the space is finite dimensional, sigma t contains only finitely many, elements. So you just take the convex hull of those. So this is a polygon. So this is a very nice elementary result that for finite dimensional spaces, numerical range of a normal operator is always a polygon. So if it is unitary, then the polygon will be inscribed in the unit circle. But look at the remark 2, there exists operator T, which is not normal, but WT is polygon. So if you look at this operator, we are considering this operator T equal to A00B, where A is this, so 0001, and B is this. Then you can see that WT is actually, since they are direct sums, so convex hull of WA union WB. So this will be convex hull of this I, this. So this is a polygon, but T is not normal. So this is how it goes on. Because of, if you look at this A operator, then this is not normal. So this is how it goes on. So this actually looks like this. So I think this will be 0, 1. This is somehow mistaken. This should be 0, 1 actually. So you should be careful. 0, 1, 0, 0. So this is actually diagonal. It should be 0, 1, 0, 0. So you can look at this. This is the numerical range of A, and this is the numerical range of B. Since the numerical range of A is already inside this, and numerical range of T is convex hull of union of WA and WB. So it's ultimately the numerical range of WT looks like this. So, but the operator is not normal because of this part A actually. So there are operators which is not normal, but the numerical range is a polygon. So now I come to the second part where I promise to talk of some fundamental numerical radius inequalities, right? And we are fortunate enough to have Professor Fuad on the this conference, so who has contributed a lot towards developing those inequalities. So the classical numerical radius inequality says that
Thank you.
uh, half of norm t less than equal to WT less than equal to norm t. So this is one of the fundamental inequalities. So WT less than equal to norm t is more or less, just a one-liner proof. And for that part, you need to do some little bit of, algebraic calculations, but not too hard. And moreover, if t is normal, then WT is norm t and RT all coincide. And if t square equal to 0, then WT is equal to half of norm t. So now I promise to talk of some particular, inequalities that have been developed using some of the techniques. First one, I focus on this Cartesian decomposition of operator, right? And for that, we'll use this convexity argument also. So, a function f on an interval is said to be convex if f of lambda x1 plus 1 minus lambda x2 less than equal to this. This is all standard, from all our usual calculus. So there is this famous result by Professor Howard, as I mentioned here, that this 1 by 4 norm of t star t plus tt star is less than equal to w square t less than equal to half of t star t plus t stars. And what has been used there, that is what I wanted to highlight, this Cartesian decomposition and convexity. So whenever you can, this is a point for those young scholars, whenever you see an inequality developed or you go through a fundamental, numerical radius inequality, you need to actually focus on what are the basic tools that have been used in that inequality, right? So what I find is that in this inequality, is very nice application of this Cartesian decomposition. I hope I have written the proof. Yeah. So suppose that T equal to B plus IC is the Cartesian decomposition of the operator. So, and if you look at this convexity of the function, then you can just look at mod of txx whole square is equal to, this bxx square plus cxx whole square. So that is again greater than equal to half of bxx plus cxx whole square. And that is greater than equal to half of b plus minus cxx whole square. So you see just simple application of this, convexity and Cartesian decomposition. So now you can look at the supremum. So supremum of w square t, as we have already known that this is greater than equal to this. So this mod of t, look at this fraction. This is greater than equal to this one. So we are just replacing this by this. Half is taken out, supremum this. So that is equal to half of w of b plus minus c whole square. And that is equal to half of w of b plus minus c whole square. So twice w square t is ultimately greater than equal to doing some calculations, b square plus c square. So that means this is equal to half of t star t plus tt star square. Tt star. So b is actually your t plus t star by 2, c equal to t minus t star by 2i. So b square plus c square comes out to be this. So this is just simple applications of very nice, very elegant application of this Cartesian decomposition. And if you look at the other way around, so then again you come to this tx whole square. So here we will be using some bxx square plus cx square. So that is less than equal to, yeah, in this step we are using Cauchy-Schwarz inequality, right? So this is less than equal to norm bx square plus norm cx square. So this is b square xx, c square xx. So b square plus c square xx. So w square of, I can see some typos. This t and a are actually same. It should be w square of t actually. So this is supremum of this. So that is less than equal to b square plus c square xx. So again, this is equal to norm of b square plus c square. So half of t star t plus t star. So you can see this very nice and elegant application of Cartesian decomposition along with this convexity argument and just one line Cauchy-Schwarz inequality. So it gives a very one of the nicest inequality in the numerical radius that 1/4 of norm of t star t plus tt star is less than equal to w square of t less than equal to half of norm of t star t plus tt star. And then again, there is another improvement of this inequality. So it is also now, there are also another very elementary identity is used, that is maximum of two scalars, a b real number, is half of a plus b plus half of mod of a minus b for a b belonging to a. So this is another nice application. So very elementary inequality to see that we'll develop this inequality. So in general, we have noticed that half of norm t is less than equal to wt. But here we can see that we can develop the wt is greater than equal to norm t by 2 plus something mod of norm of real t minus norm of imaginary 2 by 2. So that part is additional part. So this is the improvement part of this classical inequality. So here also, again, you just look at, we are going to this Cartesian decomposition, right? Instead of b and c, we are writing it real part of t and imaginary part of t. So here also we can see that wt is greater than equal to real part of norm t, near part of imaginary t. Then you just apply that max of a comma b. So this is just application of that we just talked of. So a plus b by 2 plus mod of a minus b by 2. So this again, you can see that this is greater than equal to real t plus I into imaginary by 2. So this part comes to norm t by 2. So there comes this. So this is simple application of that real number inequality, which improves this, lower bound of the numerical radius. And from there, we can see that if wt equal to norm of t by 2, then this has to be equal. Norm of real t is equal to norm of imaginary t is equal to norm of t by 2. That all things has to be equal. So this is very simple if you look at this inequality, because wt is always greater than equal to this, that is always greater than equal to norm t by 2. So if this left-hand side wt is equal to right-hand side norm t by 2, so that will squeeze them. So this part has to be 0 so that all they coincide. So this is the proof. Then another improvement from this, result that was developed by Professor Kitana. So W square of t is greater than equal to 1 by 4 t star t plus t star plus half of modulus of norm of real part of t whole square minus norm of imaginary part of t whole square. So again, we use Cartesian decomposition. So this Cartesian decomposition will allow us to show this very simple. So W square of t, now we take this is greater than equal to this. So again, we get into this. Just this time last time it was Wt greater than equal to max of norm of real t, norm of imaginary t. Now we have just taken the square one. So again, we are applying the same real number inequalities. So maximum of AB greater than equal to A plus B by 2 plus mod of A minus B by 2. So now you can again see doing some calculations. This comes out to be true. So norm of this 1 by 4 t star t plus t star plus this one. So this just very typical of those inequalities using Cartesian decomposition. Next, we show some inequalities developed using Cauchy-Schwarz and their generalizations. So for Cauchy-Schwarz, xy less than equal to norm xy, and which was very elegantly improved by Bujano, and it says like this: if xy belongs to H with norm equal to 1, then xy is less than equal to half of norm of x into norm of y plus inner product modulus of x and y. So using this, we can now develop some inequalities. So you can see what I am again saying. Professor Fuad and Umar actually proved this. W square of t is less than equal to half of W of t square plus 1 by 4 mod of t square plus mod t star whole square. So again, just we need another inequality here also. So that's Holder-McCarthy inequality. That is very fundamental, that for positive operator, txx to the power r is less than equal to t to the power r xx when r is greater than equal to 1. And it will be greater than equal to t to the power r xx if your r is in between 0 and 1. So now we prove this with the help of those inequalities, Bujano's inequality and Holder-McCarthy inequalities. So we can prove this result, that mod of txs to the power 2r is less than equal to half of mod of t square xs to the power r plus 1 by 4 mod of t into to the power r plus t star to the power r xx. So this result was already proved for r equal to 1 actually. So we are now generalizing it for r greater than equal to 1. So again, you just use this a equal to tx, b equal to t star x, and e equal to x in Bujano's inequality, which is 5. Then we get this inequality, and again convexity of the function f equal to tr, we get this inequality, and from these two we can move to show that mod of tx to the power twice r is less than equal to these quantities, and that will again lead us to this inequality. So, going on with these Cauchy-Schwarz inequalities, Bujano, there are many such inequalities have been developed. So we have to, again, I say, we have to focus on which inequalities have been used in developing those numerical radius inequalities again and again. So again, there is another example of application of this Cauchy-Schwarz inequality to develop this. This is W of t to the 2 to the power rt less than equal to alpha by 2 W of r t square, and this alpha by 4 into this plus this. So this is, here is the inclusion of this number alpha. Alpha is a number between 0 and 1. So again, we start with, Cauchy-Schwarz inequality. Now here actually the trick is you just break it, this quantity tx's, and look at the trick. This quantity is actually broken into two parts, alpha of mod of tx's plus 1 minus alpha of mod of tx's. So that again less than equal to alpha into mod of tx's plus 1 minus alpha into, now here you are using it Cauchy-Schwarz actually. So you take this x t star x, then this is less than equal to norm of t star x. So those tricks are actually very important. So then again, you just use this convexity function, mod of tx is to the power twice r. You can show that this is less than equal to this. So again, this very important that in developing those numerical radius inequalities, that you know how to use those tricks actually, right? So when you need to break up those into alpha plus 1 minus alpha, when you need to use these Cauchy-Schwarz or Bujanos or maybe Cartesian decomposition, that is very important. You need to know how to use those things. And this is a simple example to show that these inequalities improve on the earlier known inequalities. And then there is another famous inequality, which is, this more or less, this Cauchy-Schwarz inequality is actually developed for operators. So, and that is something like this. So if T is a bounded linear operator, then mod of Txx is less than equal to mod Txx to the power half, mod T star xx to the power half. And if you look at this mod Tx y whole square, then this is equal to mod T to the power 2 alpha xs and mod T to T star 2 to the 2 1 minus alpha yy. So this is actually, if you take T equal to y, this is nothing but your normal Cauchy T equal to y, it will give you nothing but normal Cauchy-Schwarz inequality. So this is again for operators T. So then again, this result was improved by Professor Fuad for continuous analytic non-negative functions on 0 infinity, right? So that's a very nice result. So if you have two functions f and g that satisfies f t g t equal to t, then this inequality is less than equal to f square mod t xs, g square mod t star yy. So this is a nice generalization of the last result. So again, using this mixed Cauchy-Schwarz inequality, you can have this inequality w square of t is less than equal to 1 by 4 mod t square plus mod t star square plus this. So again and again, you need to apply this Cauchy-Schwarz and Bujanos so to get this inequalities, right? So these are very nice, I'm not getting into this again and again, so it look very monotonous. So I'm just skipping those few things, right? So, but you can actually know how to use this and get this results. Another result of using this generalized Cauchy-Schwarz inequality and convexity of functions. So how you should use and you get these results. So these are the results which actually shows some improvement of the earlier known results. And another fundamental, actually, I will not say it's a very well-known Barnum-Smithy's inequality. Here also, you say, I'll just say 2 or 3 points here. So this was developed by Barnum and Smithy long back, right? And it was developed from where? It was developed from this identity, actually. So if lambda and theta are real numbers, lambda is not equal to 0, then you look at this norm tx square plus e to the power twice I theta t square xx is equal to this. So this is a very, if you break it up and do this plus minus and all this business, then you'll land on the left-hand side. So from there, they have proved that this results, right? Just using this, tyy is less than equal to wt into norm of y square for all y. So they have used this norm tx square plus this is less than equal to this. And from there, they have proved that norm of tx square plus t square xx is less than equal to twice w to norm tx norm x. So then, and from there, you can develop some inequalities, right? So w of t square is less than equal to this because this is norm tx. So if you cancel norm tx, if x is not equal to, so then you can develop some inequalities from here. So what I wanted to highlight here, so you see this was the inequality developed by Barnum and Smithy's, and this was the equality used, right? So what was the next step to be done to improve this or generalize this? That is what I do want to highlight. So you can just look at this. Now what we do, actually, we just take you to operator level, right? So now I take 3 operators, A, T, and B. Then I notice that this inequality is equally holding actually for all x. And for there, what I need is that the equality that was holding here, So I have to develop an equality like this involving A and B, and T is already there. A and B I am actually introducing. So what this is the truth, right? So if you take this type of thing, so when your A equal to B equal to Y and phi is 0, then you land to this Barnum-Smith equality, right? So what is the advantage of doing this equality? So advantage of doing this equality is that from there, I can actually develop some lower bounds which improve on the classical bounds. So that I will show you right now. So this is where I can. So WT is greater than equal to these things. So this is where this actually develops. So if you take A equal to T and B equal to Y, you again land into this. So this is these are some observations from my side. So when you see classical inequalities, you first need to understand what are the main tools used there and how can we generalize or improve on these. So we need to focus on, maybe for vectors it is there. So now we can look for operators. And if it is for operators, then we can look for operator matrices, block matrices. So this is how things go on actually, right? Now I have 5 more minutes, so I will go to some problems since Professor Fuad is there. So I will not miss this opportunity to discuss some problems. So I'll go to these problems directly, right? So I have more or less 5 minutes, Professor Baid.
Yes, 3 minutes, but we can give you another 5 minutes
Okay.
because it's very interesting. Thank you.
Okay, so I'll go to this. Problem 1. So we have bounded linear operator T, and we know that WT is greater than equal to half of T star T plus T star to the power half, greater than equal to norm of T by 2. So a well-known characterization of the numerical range states that WT equal to norm of T by 2 if and only if WT closer is a circular disk with center at the origin and radius norm T by 2. For young scholars, if you want to look at the proof of these results, you can look at the book by Gao and Hu actually, right? Numerical ranges. There is a very nice book by Gao and Hu. So I'll show you in the reference. So the question is, we have proved that WT closure is contained in a closed circular disk and contains a semicircular disk with center at the origin and radius this, if and only if the numerical radius attains its lower bound half of this. So the inequality, you look at this inequality, WT is greater than equal to half of T star T star to the power half greater than equal to norm of T by 2. So whenever WT is equal to norm of T by 2, then this characterization is already there. And we could prove that W2 is equal to this left. If this is equality, then this WT closure is contained in a closed circular disk and contains a semicircular disk with center at the origin and radius half. So the question now that raises in my mind, in our mind, is that whether this will again force it to be a circular disk. We could not prove it. We could prove that if it attains the bound half of T star T plus T star to the power half, then the numerical range closure is contained in the unit circular disk, and it is more than a semicircular disk. It's more than a semicircular disk, but it is within a circular disk. So my question is now, does this equality imply that this is a closed circular disk? If not, then where is an example? Now situation may be more complicated like this. So there may be some lower bound L of T, which is lying in between WT and this. We don't know because we are going on improving bounds. We don't know whether there will be another lower bound. So if we can found some lower bound improvements, the WT is greater than equal to LT is greater than equal to this, then whether WT equal to LT will characterize that the closed numerical range is again a circular disk with center at origin and radius LT. So that is the question. So the question again, I iterate, WT equal to norm T by 2 implies numerical range is a circular disk. The closure of the numerical range is a circular disk with center at the origin and radius norm t by 2. So when you improve on the bounds, whether the same characterization will hold or not, that is the main question. So, but we could not find an example that it is not a circular disk. Neither we were able to prove this, that it will be like this. It will be closed circular. So that is question number 1. And for question number 2, so if you look at MNC, so now we are working on finite dimensional spaces. So then WT is less than equal to norm T. And using that, as we said, this alpha and 1 minus alpha, we could prove that WT is less than equal to alpha of T star T plus 1 minus alpha T star to the power half for all alpha belonging to 0, 1. Also, it is easy to observe that if T is a normal matrix, then this equality holds for all alpha. Now, the question is whether this equality holds for non-normal matrices also, whether there will be a non-normal matrix which gives this equality. Z W of T will be equal to this. So whether the above equality holds for non-normal matrices for all alpha. This is true for normal matrix. If T is a normal matrix, then this is true for all alpha. So whether non-normal matrix, in a way we can say that whether this is a characterizing property of normal matrix or not. So if it is true for all alpha, whether T is a normal matrix or not. So that is the same way that the question 2 is being written over here. So whether the above equality holds for some non-normal matrix. So that is also not known to me. And maybe problem 3. Maybe we continue with this. For a normal matrix T, this is this. So what is the boundary of the numerical range? So is not smooth. So if you are looking at this finite dimensional normal matrix, as we have proved that this is all polygon, so boundary is not smooth. So these endpoints or vertices are actually non-smooth points. So also we can find non-normal matrix for which boundary of WT is not smooth, for which WT is this. So if you look at this example, 0, 2, 0, 0, and then 2, so this looks like this. So this is not smooth. So this is not smooth. So in this contest, question is this. So what can you say if this relation holds about the boundary? Whether the boundary of the numerical range will be smooth or not. So this is another, questions that I wanted to discuss. So this is all I wanted to say. Maybe I will go to the references. So you can see lots of papers of Professor Fuad and our group. And I would like to highlight some books. This is one book. It's a famous book by Gustafsson and Rao, Numerical Range, Inequalities and all these things. They must have this book. Then there is, I believe, this book by Gao and Hu also, right? It should be there. This one I was talking of, Gao and Hu. This book is also very nice. So it's very interesting. You should have a look at this. And you can also look at this book. I don't know how these writings are coming. So if you can have a look at, you can also have a look at this book by, this Bunia, my student, Professor Dragomir, Professor Moslian, and myself. This is recent one. It's published in 2020, where we have discussed numerical radius, mostly numerical radius inequalities. And the other 2 books are on actually numerical ranges, more or less, analytical properties of numerical ranges. So that's more or less. Thanks for your kind attention.